You can fly to clouds, you can walk into rain, but you can't go to a rainbow. Try it retreats like it's alive. And here's the uncomfortable part. If you and a friend stand a few steps apart, you are not even looking at the same one. So where is it? You're standing there after the rain. Sun is out again, and suddenly there it is, a rainbow, hanging in the sky like somebody painted a giant curved stripe and forgot to erase it. And your brain does something automatic. It treats the rainbow like a thing, like a real object sitting out there at some location, somewhere beyond the trees, somewhere above the hill, something you could point to and say it's right there. In fact, most of us try to do the childish version of science. You see the rainbow and you decide to go get it. You walk toward it. You expect it to grow bigger, get closer, maybe touch the air where the colors are, and it never works. You walk and walk and walk, and the rainbow stays the same distance away, or it fades, or it shifts to some other spot like it's teasing you. So the first problem is simple. Why can't you go to a rainbow? Not because it's far, not because it's in the sky, because you can go to the sky in an airplane, you can go to clouds, you can go to rain, but you cannot go to a rainbow. That should bother you, because physics is usually cruelly honest. If something is there, you can at least in principle go there. You can chase it with a drone. You can triangulate its position. You can measure the distance. Try that with a rainbow. Where exactly is it? Point to a place in space. Give me coordinates. Latitude, longitude, altitude. Where do the colors live? You might say in the raindrops. Reasonable guess. The rainbow appears when there are water droplets in the air and sunlight behind you. So maybe each droplet is like a tiny colored lamp, and together they make the arc. But then you notice something that ruins the object idea immediately. Two people standing a few meters apart do not see the same rainbow. They'll both say they see a rainbow, sure, but the actual set of droplets sending the red light into your eyes is not the same set sending the red light into your friend's eyes. The geometry is different. Your head is in a different place. The lines from the sun through the droplets into your eyes are different. That means the rainbow you see is not a fixed thing in the sky. It's a viewing condition, a relationship between four ingredients. 1. The sun. 2. Water droplets. 3. Your eye. 4. Geometry, pure cold geometry. And this is the slap in the face part. The rainbow is not out there in the way a cloud is out there. The cloud is a physical object. You can fly through it. You can scoop some water out of it. Everybody agrees where it is. The rainbow is more like a direction. It's like the glint on a shiny car. You know that blinding flash you get off a windshield. You think it's sitting on the glass like a sticker. But if you move your head, the flash jumps. You can't walk up to the flash and grab it. The flash is not a thing. It's light coming to your eye at a special angle. A rainbow is that idea, but in 3 dimensions, with millions of droplets acting like optical machines. Now here's the second problem, and it's even weirder. If the rainbow is just sunlight interacting with droplets, why does it have that precise shape? Why an arc? Why those colors in that order? Why does it look like a circle when you see it from an airplane? And why does it seem so stubbornly locked in place relative to you? You turn your head, it turns with you. You take a step, it follows. It behaves like it's attached to your line of sight. So let's make the confusion clean. We have an everyday picture, rainbow equals sign a colored object in the sky. But we have 3 facts that don't fit that picture. Fact 1, you can't reach it. It retreats as you approach. Fact 2, 2 observers don't share one rainbow. Each person gets their own. Fact 3, the rainbow's position is determined by your viewpoint. Move your head, it shifts accordingly. Those 3 facts are screaming the same message. Stop treating it like an object. So what is it, physically? To answer that without getting lost, we need to be clear about what seeing even means. Seeing is not magic. It's not knowing. It's receiving photons, little packets of electromagnetic energy into your eye. When you say, I see a red stripe, what you really mean is light of certain wavelengths is entering my eye from a certain direction. Direction matters a lot because your eye doesn't detect where things are directly. Your eye detects angles. It's basically an angle measuring device with a biological screen inside it. Your brain then pretends those angles correspond to objects at definite locations. Most of the time that pretending works beautifully. If I see a tree at a certain angle and I walk toward it, the angles change in the way they should for a real object. So my brain is trained, angle patterns that behave consistently are things. But a rainbow is an angle pattern that behaves consistently without being a single thing in space. It's an illusion in the precise, respectable physics sense, not fake, not imaginary, not in your head, but dependent on the conditions of observation. Now, when people hear illusion, they think not real. That's a mistake. The rainbow is completely real light. It will show up on camera. It will show up for any animal with eyes. It obeys optics perfectly. The illusion is only in the location. The colors are real photons. The place where the rainbow is not a place. So here's a way to think that forces your intuition to behave. Imagine you freeze the whole scene, the sun behind you, and in front of you a huge volume of air filled with droplets. Millions and millions, like a three-dimensional swarm. Now draw a line from your eyes straight through the center of the rainbow. That line points to a direction in space. Along that direction, at many distances, there are droplets. Near droplets, far droplets, droplets at all sorts of ranges. Some of those droplets will send light into your eye at just the right angle to be red. Some will send light at just the right angle to be green. Most won't. The rainbow appears where there is a dense set of directions for which droplet plus sunlight produces light into your eye at particular angles. Notice what's missing from that description. A single distance. The rainbow is not at 5 kilometers away or 500 meters away. It's a set of rays entering your eye, organized by geometry. And that's why you can't get to it. When you walk forward, you change the geometry. The droplets that used to send red light into your eye no longer have the correct angle. But somewhere else, new droplets, different ones now do. So you keep receiving the same directional pattern, but from a constantly changing population of droplets. You aren't chasing a thing. You're chasing a condition. It's like chasing the place on the ground where your shadow's head touches. You walk toward it, and it walks too. There's nothing to pick up. Now, we're not going to do the full optical machinery yet, how the angle comes out around 40-something degrees, why the colors spread, why there's sometimes a second rainbow, reversed, fainter, with a dark band between. That's part 2, where geometry does the heavy lifting. But we can already define the core claim so you know what we're aiming at. A rainbow is not an object in the sky. A rainbow is the set of directions from which light reaches your eye after being refracted, reflected, and refracted again inside water droplets at very specific angles. And once you accept that, everyone has their own rainbow idea, stop sounding mystical and start sounding inevitable. Because the key ingredient is not the droplets. The key ingredient is the droplets relative to your eye. Change the eye, you change the selection rule. Different droplets satisfy it. Different rays enter. Different rainbow. So when two people stand side by side, they're not sharing a single distant arch. They're each sampling a different cone of directions through the droplet field. The arcs overlap visually, but physically they're built from different light paths. That's the problem definition. That's the mental trap. Your intuition wants the rainbow to be out there. Physics says the rainbow is a relationship, not a location. In the next part, we're going to earn the geometry, not with fancy math, with a simple droplet, a few rays, and the kind of angle chasing that makes the universe feel mechanical again. Because once you see the mechanism, you'll realize something quietly profound. A rainbow isn't in the sky. It's in the rules of how light is allowed to arrive at you. So let's build the rainbow from one droplet. Just one. A tiny sphere of water hanging in the air like a little glass marble. Sunlight hits it. White sunlight. And white isn't a special color. It's a mixture. A whole stack of wavelengths, from red to violet, all traveling together. Now the droplet does 3 simple things to a ray of light. First, it refracts when entering. It bends. Second, it reflects off the inside surface. Third, it refracts again when leaving. That's it. No magic. No quantum weirdness. Just geometry plus the fact that light changes speed when it goes from air into water. And that one fact, light changing speed, produces refraction. The ray changes direction because one side of the wavefront slows down first. It's the same reason a marching band turning a corner bends. One side hits mud, slows, and the whole line pivots. Now here's the key. Not every ray that enters a droplet leaves it in a direction that matters to you. Most rays leave at some random angle that doesn't point toward your eye. But there's a special range of angles where something weird happens. Many rays bunch up and come out nearly parallel to each other. When that happens, your eye receives a lot of light from that direction. Brightness, a sharp edge, a stripe. That bunching up is the whole rainbow. So let's chase a ray. Picture a ray of sunlight hitting the droplet a little above the center. It enters water, bends toward the normal, travels inside, hits the back surface, reflects, then exits, bending away from the normal. You can define an angle, how far the outgoing ray is deviated from the direction it came in. Call it the deviation angle. If the incoming sunlight is basically parallel rays, the sun is far away, so yes, then the droplet is like a machine that takes parallel rays and spits them out in various directions depending on where they hit. Now vary where the ray hits the droplet. Higher, lower, closer to the edge, closer to the center. The deviation angle changes. Most of those deviations change smoothly, but around one particular value, the deviation angle reaches a minimum, a turning point. That matters because near a minimum, lots of different incoming rays produce almost the same outgoing direction. It's like a traffic system where many side streets feed into the same highway lane. More rays per angle means brighter light in that direction. That bright direction for the primary rainbow ends up being about 42 degrees from the exact opposite of the sun. Not from the sun, from the anti-solar point, the point in the sky directly opposite the sun, right in the middle of your shadow's head. If the sun is behind you, your shadow points forward. Extend a line from your eye through your shadow's head and into the sky. That direction is the rainbow's center. The rainbow is a circle around that point, and the radius of that circle is about 42 degrees for red light. A bit less, around 40 degrees for violet.
Now, this is already enough to explain the you can't go to it problem. Because the rainbow is not a point, it's a cone of directions. Take that 42-degree angle. Imagine a cone with its tip at your eye, axis pointing to the anti-solar point, opening angle 42 degrees. Every direction on that cone is a possible direction from which red light can arrive after doing the droplet trick. Where that cone intersects the field of droplets, you get a visible arc. No droplets in that direction, no rainbow there. Plenty of droplets, bright rainbow. But the angle is the boss. The distance is irrelevant. Now the colors. Why does red appear on the outside and violet on the inside? Because water refracts different wavelengths by different amounts. That's dispersion. The refractive index of water is slightly larger for violet than for red, meaning violet light slows a bit more, bends a bit more. So in the droplet, violet rays deviate more than red rays. Their minimum deviation angle is smaller. So the cone for violet has a smaller radius than the cone for red. Concentric cones, concentric circles on the sky. Red outer edge, violet inner edge. That's not a poetic statement, that's geometry. Now why is there a sharp edge? Why doesn't the whole sky become a smooth wash of color? Because of the turning point. The minimum deviation creates a pileup. On one side of that angle, rays exist. On the other side, they don't, or they're sparse. So there's a bright rim, then rapidly less light just inside it, and almost nothing just outside. And you can feel the consequence. The rainbow is bright because nature is wasting lots of rays into your eye from a narrow range of directions. Acoustic, like the bright squiggly lines at the bottom of a swimming pool. Same idea, geometry concentrates rays. Now let's take it up a level. One droplet gives you a preferred outgoing direction for each color. But you're not looking at one droplet. You're looking through a cloud of them. Millions, maybe billions. Each droplet is sitting somewhere in space. And each droplet can contribute to your rainbow only if it lies on the correct cone for that color. So your red rainbow isn't made by all droplets. It's made by the droplets that happen to lie on your red cone. Your green arc is a slightly different cone. Your violet arc is tighter. That's why the rainbow has thickness. And that's why your friend's rainbow is different. The cone's tip is at the eye. Move the eye, move the cone. Different droplets qualify. Same angle rule. New physical contributors. Now we can handle another thing people notice and then ignore because it's too strange. Sometimes there's a second rainbow. Fainter, larger, with colors reversed. Where does that come from? Same droplet, same sunlight, but instead of reflecting once inside the droplet, the ray reflects twice. Enter, refract, reflect, reflect again, refract out. Two internal reflections means more loss. Light is weaker each time, so the second rainbow is fainter. But the geometry now produces a different minimum deviation. The outgoing rays bunch up around a larger angle from the anti-solar point, about 51 degrees for red, around 54 for violet. And because the dispersion plays out differently, the color order flips. Red ends up on the inside of the secondary bow, and violet on the outside. So now you have two cones, the primary around 42 degrees, the secondary around 51 degrees, and between them, often a darker region. Alexander's dark band. Why darker? Because for the primary rainbow, rays do not emerge at angles larger than the minimum deviation angle in the relevant way. For the secondary, rays do not emerge at angles smaller than its own allowed range. There's a gap in ray density between the two pileups. Not because the sky is darker there, because the droplet optics sends less light into that band of directions. The sky isn't painted, it's illuminated.
Now why is the rainbow an arc and not a full circle?
Because the ground gets in the way. The full circle exists, but half of it is below your horizon. If you're on a mountain with droplets below you, you can see more of the circle. From an airplane with droplets beneath, you can see a complete circular rainbow, often around the plane's shadow on the clouds. Again, center is the anti-solar point. The rainbow is locked to your shadow, not to the landscape. That's such an unsettling statement that it deserves to sit there for a second. The rainbow is centered on your own line to the anti-solar point, meaning it's centered on you in a geometric sense, not because you're special, because your eye is the detector, and geometry cares where the detector is. Now, a common wrong picture is, the sun sends a beam, it hits the droplets, and the rainbow forms over there. No. The correct picture is droplets are everywhere, doing their droplet thing in all directions, but you only see the ones that send light into your eye at the special angles. The rainbow isn't an emitter, it's a selection. Your brain then stitches those selected directions into a smooth arc, because your eye sweeps across directions continuously. Millions of droplets at slightly different positions satisfy slightly different directions, and the result looks like one continuous band. Now here's a subtle thing that makes the whole experience feel personal. If you're looking at a rainbow, the middle of it, the point it's centered around, is a point you cannot see directly unless you look at your shadow. It's behind your head in a way. It's the direction opposite the sun, which is behind you. So the rainbow is a ring around a point defined by you and the sun. That's why it follows you. Turn, it turns. Step, it steps. And now we can sharpen the original claim so it stops sounding like a cute slogan and starts sounding like a physical statement you could defend at a blackboard. A rainbow is not located at a distance. It is located at an angle. It is a caustic produced by refraction, internal reflection, and dispersion in spherical droplets, observed along a cone of directions centered on the anti-solar point. And if that sentence feels too technical, good, because the universe is technical, but the picture is simple. A cone from your eye. Droplets on the cone. Bright rim. Now there's one last irritation we have to face before moving on. If the rainbow is just geometry, why does it sometimes look super vivid and sometimes washed out? Why does it sometimes have extra faint bands inside? Why does it sometimes appear even when the rain seems far away? Those aren't philosophical questions. They're about the droplet size, the distribution, the background brightness, and a little bit of wave interference riding on top of the ray picture. And that's where the story gets even more interesting, because the ray explanation is almost correct but not perfectly. Nature always leaves a catch. In the next part, we're going to push on the weak points, why the rainbow has a width, why supernumerary bows exist, and how the same physics explains why everybody owns their rainbow, yet you can photograph it and prove it's not in your head, because the rainbow isn't a myth, it's a law of optics wearing a costume. So let's push on the weak points, because if you stop at the ray tracing story, you'll have a nice picture, but you'll miss why the rainbow sometimes looks like it has extra stripes, why the edge is so sharp, and why the world is annoyingly more precise than our simple drawings. First, the rainbow's thickness. In the ray picture we said there's a minimum deviation angle, so rays pile up. True, but they don't pile up into an infinitely thin line, because real droplets are not perfect identical spheres in exactly the same place, and sunlight is not a perfectly thin beam, and your eye is not a perfect angle detector. Everything has a spread. Also, different rays that enter at slightly different impact points come out with slightly different deviations. Near the minimum, that change is slow, but it isn't zero. So the bright region has a finite angular width. The rainbow is thick. Second, the rainbow's vividness. Some days the colors look like they were printed. Some days it's pale, almost ghostly. That has less to do with your imagination than with the physical size distribution of droplets. Tiny droplets, mist, fog, spray, scatter light more diffusely. The rainbow becomes whiter, the colors blur, because the scattering is strong and the geometry is less clean. Larger droplets, fresh raindrops, behave more like good little lenses. The caustic is sharper, the colors separate better, the bow looks more saturated, and background matters too. A rainbow is not a light source in isolation, it's a contrast phenomenon. Put bright gray clouds behind it, and you lose it. Put dark storm clouds behind it, and suddenly it burns. Third, those extra faint bands inside the primary rainbow. Sometimes you'll see them, a couple of thin pastel stripes tucked just inside the violet, like the rainbow has a secret second set of rings. Those are called supernumerary bows, and they are the moment the rays story confesses,
It's an approximation, because supernumerary bows are interference. They are wave behavior. Here's the idea. In the ray diagram, you can have multiple paths through the droplet that send light toward your eye at nearly the same angle, slightly different entry points, slightly different travel times through the water. In the pure ray picture, you just add intensities and you get one bright rim. But light is a wave, and waves don't just add, they interfere. If two wave contributions arrive in step peaks with peaks, you get reinforcement, brighter. If they arrive out of step peaks with troughs, you get cancellation, darker. Near the rainbow angle, the path lengths vary smoothly with the impact point. That means the phase differences vary smoothly too. So instead of one smooth bright region, you get oscillations, bright dim, bright dim. Those oscillations are the extra bands. And notice what that tells you. The rainbow is not just pretty, it's a measurable signature of light's wave nature and the droplet's geometry. You can predict where those bands appear based on droplet size and wavelength. The rainbow is a physics experiment happening in the sky with no lab coat. Now, do these extra bands ruin the main claim that the rainbow isn't in the sky? They actually strengthen it, because interference patterns are the ultimate viewing condition phenomena. Like the fringes in the double-slit experiment, the pattern is not a thing sitting on the screen waiting for you. It's the consequence of waves arriving at different angles and adding. A rainbow is in that sense a gigantic outdoor interference and refraction machine. Now let's go back to the question that started the whole trouble. Why does everyone have their own rainbow? At this point the answer should feel almost boring, because the bow is tied to the anti-solar point, which is tied to your position. Your eye defines the tip of the cones. Your line to the anti-solar point defines the axis. The droplets are just the material that happens to be available to satisfy the geometry. So two people don't share a single arc in space any more than they share the same exact glare off a lake. They can both see a glare. They can point in roughly the same direction. But the specific photons entering one person's eye are not the same photons entering the other's. And that creates a surprisingly intimate fact. The rainbow is not owned by the landscape. It is owned by the observer. Not in a mystical way, in a geometric way. Now a reasonable person might object, hold on, if I take a photo of the rainbow, it's still there.
Correct. It is not in your eye. It is not a hallucination. The camera is another detector. Put it where your eye is, it sees the same cone of directions. Move it, the cone shifts. If you put two cameras a few meters apart and photograph the rainbow, both images will look similar. That's because the cones are similar and the droplet field is dense. But the exact set of droplets contributing is different. And that's the punchline. The rainbow is real light in the world, but the where of it is not a location, it's a rule. Now this also explains the one thing people never think about until you force them to. What would you see if you could hover in place and remove all droplets except one? You would not see a rainbow arc, you would see a bright colored point, or nothing, depending on whether that one droplet happens to send the right color into your eye at the right angle. The arc requires a whole field of droplets to fill out the cone. The geometry is simple, but the scene is statistical. You need enough droplets that every direction on the cone has some droplets sitting there. That's why rainbows love showers. Lots of discrete drops floating in space, each an optical factory. And it gives you a weird way to imagine the world. You can look at a rainbow and think there are countless droplets out there, and only a thin subset, those lying on a very specific cone, are participating in what I'm seeing. The rest are doing their own thing, sending light elsewhere. Reality is not organized for you. You are sampling it. Now let's do the existential zoom out, because if we don't, we've just done optics and missed the real point. The rainbow is a perfect example of something the universe does all the time. It tricks your intuition by giving you a stable pattern that looks like a thing, even when it isn't a thing. Your mind is an object factory. It wants nouns, it wants locations, it wants solid stuff. But physics often speaks in verbs and relationships, fields, waves, probabilities, constraints, symmetries. A rainbow is the friendly, colorful version of that lesson. It's the universe saying, stop asking where it is, ask under what conditions it appears. And if you learn to ask that question, you start seeing the world differently. You start noticing that many things are really conditions. A shadow, a reflection, a glare, a mirage over hot asphalt. Even the blue of the sky, another scattering and angle story. Not a blue dome, a distribution of light. So next time you see a rainbow, try this. Don't look at it like a bridge you could walk on. Look at it like a diagram you are standing inside. The sun behind you, a point opposite the sun in front of you, a cone of angles around that point, droplets scattered through space, and your eye sitting at the tip, selecting which photons count as the rainbow.
That's all it takes to make an impossible thing appear, a circle of color with no location. And that's the beautiful part. The world can create something you can see clearly, photograph, remember forever, without ever placing it anywhere. If you want to keep going, if you like this style of physics where we treat your intuition as the enemy and then rebuild it properly, stick around. There are a lot of objects in your everyday life that aren't objects at all. And once you learn to spot them, you don't just learn physics, you learn how reality actually behaves when nobody is trying to make it easy for humans.